Vectors are fantastic. It's a data structure that allows us to change how much data is inside of it, a container that allows us to adjust how much data is inside of it at any given time. Vectors can increase and decrease in capacity. We can store almost any type of data into it, and it's in a contiguous block of memory. And some of the great things about vectors is because it's in this contiguous block of memory, it's really quick to access individual elements. We know this memory location. Typically, we hold a pointer to that position, and we want to know an element that's further on down the chain in this contiguous block of memory. It's really easy. The subscript operator for this becomes pretty trivial. It ends up being our data pointer plus the index that we want to search for, and then we dereference that position. That's pretty much it. It's one line of code. It's one really quick addition. You take this memory address, you add a number to it, just doing some pointer arithmetic. You dereference that memory address, and you have the block that you need. It's so quick. Well, why would we use anything else? Well, vectors are also really slow. They're really slow when we want to insert something here at the beginning. Remember the case of, hey, we have a bunch of data here. It might look something like this, and we are at our capacity. And I want to insert something right here at the very beginning. This is sort of the worst case scenario for vectors. Well, what do I need to do? First thing is I need to allocate a whole new block of memory somewhere else that has a much larger capacity. Then I have to copy every single one of these elements to the new position, right? To the new location of memory. Then, most likely, because I need room for this first element, I'm gonna have to shift every single element down by one, something like this. Then finally, I can take my new element and add it right here at the very beginning. That was a lot just to insert one piece of data at the very beginning of this entire block of memory, right? It's a lot of work. This function actually ends up being really slow because of that. But this function is really fast. So vectors do have their pros and cons. And a large part of it is because of how we've built this, using a contiguous block of memory. Well, what if we needed some sort of storage container that we were constantly adding and removing elements from? It would kind of be like the worst case scenario for vectors. We'd be doing this all the time, and our functions and our program would probably be really, really slow. What we really need is something that avoids this situation. Let's think about a data structure that could potentially avoid this situation. Well, we know it can't be in a contiguous block of memory. It just can't, because there's no room for us to put data at the beginning, right? We can't allocate memory backwards. It's just not really possible. So we need to sort of break up what we think of as storing something in memory. Let's think of how we could do that. Say we had an element in memory that looked like this. Here's our number 5. And we want to break this thing up. Here's our number 6. If each element of our container was at a different place in memory, right? It wasn't in a contiguous block. And if these things sort of knew where the next element was, here's the first one. The next one is a 6. And the next one's up here, number 7. And I want to put another one at the very end, and I say, okay, here's another block of memory block 8, and it goes here, right? Well, if we devised a container that looked something like this in memory, with each individual element somewhere random in memory, and each element sort of pointing to the next one, so we knew how to traverse it and get to each of the elements, right? This would make it really easy for us to insert data at the very beginning of this thing. Imagine we want to insert the number 4 at the beginning. Well, it's easy. None of these things need to move. None of these things need to change. We just find a new place in memory. Here's the number 4. And we say, the one after you is this one, the original number 5. 2 operations, real quick. Create a new element. Make sure we hold on to this. We're done. We have this sort of system where it's not using a contiguous block of memory. And it's really quick, potentially, to insert and also to remove elements. We want to remove this number 6. In the vector, we would have had to shift all the elements down to maintain that they're all in this contiguous block of memory. Well, using a system like this, if we want to remove an element, we just delete that one element, and then we update this sort of reference, this thing that we're holding on to, right? Whatever it is, however we keep track of what's next or what's upcoming, right? This strategy, surprise, surprise, is called a linked list. Linked lists are data structures that look like this. They are not in a contiguous block of memory. They are sort of scattered. So one of the implementation details is instead of allocating a large block of memory, you are allocating individual pieces of memory. In addition to this, each node, which are what these are called nodes. Each node in our linked list needs to keep track of what's next, what's coming up, where the next thing is, where the next element is, right? And then our linked list data structure itself, well, it just needs to keep track of, like the vector. The vector just kept track of the first position, the very beginning. It's just a pointer to the beginning of this contiguous block. The linked list can keep track of this, a pointer to this one, the very beginning, right? It'd be a little silly if it had to keep track of pointers for every single one, because then we're talking about, having a vector of pointers inside our linked list. That doesn't make sense at all. We want our linked list just to have one pointer at the very beginning. This makes it really easy for us to add and remove elements without having that huge overhead that we have with the vector. Well, there's some really good benefit there. Now if we're writing code and we're writing a program that is constantly adding and removing elements, you're working on the multiplayer system for an MMO, and there's players constantly being added and removed from the matchmaking system, and you need to match these things up. And so you're removing players as they find games and matching players with other ones, and you are adding and removing players all the time. You probably want to use something like this, like a linked list, as opposed to a vector, where you constantly need to be resizing this thing back and forth, right? Well, what are the downsides of linked lists? If we have a structure like this, one of the downsides is, well, remember that really quick subscript operator when we knew exactly where everything was because it was in a nice contiguous block of memory? We don't have this here. Well, how do we figure out where the third element is if we want to do subscript 3, or the fourth element if we want to do subscript 3? Well, to find that element, we got to start here at the beginning. And we have to go to the next one, and then to the next one, and then to the next one, right? We are essentially turning our super quick algorithm, our super quick subscript operator, into essentially a for loop. This thing's going to become a lot slower. So linked lists are great when it comes to adding and removing, but it's going to be a lot slower when it actually comes to accessing these individual elements, just because of this need to sort of hop between them. Now, each one of these nodes is also going to have to store a little more data, right? Remember with our vector, when we had that contiguous block of memory, inside that block of memory, it was just whatever our element was. If we're holding integers, it's just our integers, 4, 5, 6, so on and so forth. In this case, our linked list needs more data. It needs to hold the value. It needs to hold that integer, the number 4, but it also needs to keep track of a pointer or something to this next block, right? So our node is actually going to end up looking something like this, where it has the data that it's holding, the value for, and then it also is going to have to keep track of the memory location, the location of the next node. It's going to need something like this. Now, this may look a little weird because you are using the class inside the class, but believe me, it works, and it's pretty cool, actually. So this is what each one of these nodes is going to look like. We're going to have our data inside of it, and then we're also going to have a pointer to the next node. This is the major difference between a linked list and a vector. It's the contiguous block of memory versus allocating these individual nodes and finding where they're located in memory and then sort of chaining them all together. It has a big impact on all the different functions that linked lists have. The add, remove, the subscript operator. And linked lists and vectors typically have almost all the same functions. You can use either to store your data. And anywhere where you're using a linked list, most of the time, you could use a vector instead, right? And reality is that under the hood, one of them is slower in some operations, and then one of them is slower in other operations. So we need to be informed about how these things work, about which functions are faster, because quite honestly, if we want to write really good code, we just need to know which data structure to pick, which container to pick. I've worked at companies in the past where sometimes we're like actually just swapping out which data structure I've used has improved the runtime of functions and runtime of programs incredibly. It's just had like a huge impact. There was a company I worked for where day one I went in, and one of the first things I did was I just kind of swapped out a couple of these data structures because I saw that things were being added, removed, or accessed really frequently, and they were sort of using the wrong one. And it just like completely sped up the program. It was a huge impact just on day one. So knowing this kind of stuff can increase the performance of all of the code that you're working on, all the containers that you're using. And just think that extra CPU time can be spent making things look better, better graphics, more advanced AI, rendering neat things, better particle effects and visual fidelity. When you're doing stuff on a mobile device or on a VR headset and you have to be rendering at 120 frames a second on on two screens, you need to have this performance. Because if you don't, then you start going down this path of, well, what can we remove from our game, right? So we want to be really good efficient programmers. We need to know the differences between these two. But contiguous block of memory, individual discrete elements, that's the fundamental difference between a vector and a linked list.